Hi, everyone. Welcome to the Protocol Labs Research Seminar Series. Today's speaker is Luca Muscariello. Luca works as Principal Engineer at Cisco in the Chief Architecture and Technology Office. His work covers research and development, as well as the industrialization of information-centric networking technologies. He previously spent 10 years working at Orange Labs, doing research and innovation in different areas of networking, such as quality of service, traffic management, and traffic engineering in fixed and mobile networks. He's a senior member of the ACM, IEEE, and SEE. He's also currently leading 2 open source projects that focus on high performance implementation of ICNs and transport stacks. And as with all of our speakers, there's plenty more to his bio, but I wanted to get right to the talk. So Luca, I'll let you take it from here.
Okay, thank you for having me. So this is an introduction to hybrid information-centric networking. It's an effort that is also open sourced. It's been incubated in Cisco and then open sourced almost 2 years ago in the Linux Foundation project, in the FDIO Fast Data project, where Cisco has open sourced several technologies in the space of high-speed software switching and routing. All right. So first of all, what is hiCN in the first place? You may have heard something about content-centric networking by Vine Jacobson, or name data networking, an NSF-funded program since 2010. So the whole idea was actually launched by Vine Jacobson at Park as a research project. And so more recently, Cisco has acquired CCN Xerox IPR. So this is almost 3 years ago. And then open sourced in Apache license the entire software and software from the Park's acquisition, and also new software developed at Cisco, in particular the hybrid ICN implementation. So hiCN, in very short, brings CCN into IPv6. And the reason of that is to try to get CCN, ICN semantics as soon as possible into the infrastructure. So it's essentially a way to bring all CCN semantics into something that can be deployed very quickly. So I don't know how much people are familiar with ICN in the first place, but ICN and hiCN is a network architecture. So it's a layer 3 and layer 4 technology. And it's supposed to serve any kind of application. So it's not just, for instance, a unicast-like protocol. It's not a something like multicast, IP multicast, where essentially IP multicast is a network architecture to serve very specific workloads and applications, and so on. So hiCN and ICN, in this sense, is really a so-called a thin waist of the protocol stack. So it's something that is supposed to serve several, actually any kind of application. So in particular, it enables connectionless and location-independent communications. I don't think I need to explain to this community what location independence means. And this is done by using network identifiers, which are unambiguous names, essentially. The protocol semantics underneath are essentially request reply. And for those who are familiar with TCP, in TCP, you send the data first, and then you get acknowledgement of reception of the data. In hiCN, the transport stacks in hiCN fetch data by request. And so instead of sending data before acknowledging it, so it's quite the opposite. So you send requests to the sender, and then you get the data from the sender. So it's something that also, from a end-to-end perspective, it realized what is called the local flow balance, which is something that has been inspired by TCP, and it's a term coined by Vine Jacobson for TCP. Flow balance means that you get the network gets the same amount of information from the ingress and this amount of information get out of the network through the egress, through the endpoints. And so global flow balancing TCP is generalized in hiCN by Vine-Jacobson by enforcing flow balance across all the different hiCN enabled nodes. The other specific characteristic of hiCN is that the authentication and integrity is a built-in features of the transport layer, which is not the case for instance, in TCP. So we don't have authenticated endpoints in TCP IP. And in the case of hiCN and hiCN in general, data is authenticated, meaning that you get from this kind of authentication provenance. So you're always able to verify that the data you fetch using a given name is actually the data the producer identity is meant to be by essentially adding signatures to the envelope that carries data and the names associated to this data. And I think this concept is also very familiar to this community. So to summarize, the hiCN in general and also hiCN essentially recenter communication on the what, so essentially names and data, as opposed to endpoint host communications. Like when you open a socket between two hosts, you need the socket address of the communication endpoints, and then you use these locators to create connections and sort of virtual wires so that the data can flow from one host to another. So what does it bring to current networking? So it brings back many-to-many communications. It simplifies anycast and multicast, so you get anycast and reliable multicast. So today it's very complex and it's very fragile to use TCP anycast, for instance. Or it's very difficult to implement reliable multicast using IP multicast. It also brings a redundancy elimination. The other specific property of hiCN and hiCN is that the data center is stateless. So which brings advantages in terms of scalability, as you don't need to store socket information on a per socket basis, on a per consumer basis, on a per client basis, but you keep socket information on that scales with data. So if you have to share a certain number of video channel or real-time channels, or a certain number of files across the network, the number of sockets you need to open is going to be proportional to the data you share, and not the number of end clients and data consumers that want to attach to this socket. And so again, so scalability for many workloads we struggle with today, like group communications, multicast, but also load balancing and anycast. So very quickly, let's try to go quickly into the details. So the core principle in hiCN is to name data. So you need, in the first place, identifiers and a network namespace that can be used to unambiguously index data. In the case of hiCN, this is done using IPv6 numbers. And as opposed to, for instance, hiCN implementations such as MDN or CCN, the network namespace in hiCN is way more short-lived, meaning that we make a very specific distinction between the application level namespaces like URI or RTP, SSRCs, or other kind of application level namespace, and the namespace that is used in the network. So which means that they are not permanent. And the hiCN namespace is reused by end host to distribute a different application level namespaces. So so this is a very significant difference with, for instance, NDN or CCN, where the application level namespace and the network namespace are the same. So how do we name data in the first place in the Internet protocol? Because NDN and CCN, they are not using the Internet protocol, they overlay on top of it, or they just replace it. In the case of hiCN, we use the existing infrastructure also because these names are routable entities. And so they are used to route requests across the network. So this is why we have decided to use IPv6 namespaces or IPv4 with extensions bits so that they can be routed across an IPv4 routing plane as well and forwarding plane as it is. But the trick, so the first change of variable we do in hiCN is to take a regular IPv6 number, which is 128 bits, and to use this number as an identifier instead of as a locator. So this is the first thing we do. And for doing that, we just use any IPv6 namespace. We don't the unicast IPv6 namespace. And we let the control plane to be aware of which part of this namespace is used as an identifier or as a locator. So, of course, this is it's something that is open in the sense that one of the main objectives at Cisco with hiCN was to have something that is quickly deployable. It does not require standardization. It just reuse or tricks the existing infrastructure so that it works. And every effort in hybrid ICN is made with a global objective to get something that can be deployed quickly, reuse software, reuse other services such as the DNS, reuse the routing plane and routing protocol existing today and use them deploy today instead of deploying and reusing new ones. But there are other possibilities like standardizing new address families and a new discovery service or a new routing protocol, but this is not what we are following. So everything that I'm going to describe in this talk is something that does not require any change in the existing network. It just requires updates in the endpoints and the applications that are using this protocol, and potentially adding new middle boxes, doing switching. So very privacy preserving, because they're just switching packets, instead of having middle boxes doing some sort of DPI to get or overlays on top of middle boxes, et cetera, et cetera. So this is something that important to take into account in this talk. So how do we do this? Well, first of all, what it is in the network layer. For those who are familiar with hiCN and NDN and CCN, this is a very very clear diagram. Essentially, you get a piece of data that is coming out of interface from a data producer or a socket producer, and this piece of data is named by carrying, as I said, this IPv6 number. And you need a request, which is a packet that is used as an index for the data packet. Essentially, this is the first component in hiCN in general. And this is common to CCN, which is now available as an RFC. And so there is a one-to-one match between a piece of data and the request data. So what we call interest packet. Then there are optimizations that we have developed in hiCN, which allows to also get flexibility in this one-to-one mapping. But I'm not going to talk about this right now. So I'm just trying to prevent questions about, do we really need to get all the overhead of having a single interest packet for every single data packet? Or another potential question that could be, is it feasible to sign every single data packet and carrying signatures of every single piece of data packet. So this is what the general architecture and principles requires. But there are optimizations that can be done in a way that it's equivalent to this general concept, but it doesn't require to sign every single data packet. But you can sign metadata packets and messages that can be used by the consumers to verify provenance of the data packet. And in the same way, there are optimization that can be done so that you can get sort of kind of a header compression styles, so that instead of having a single data interest packet for every single, a single interest packet for every single data packet, you can get also optimization to relax this constraint. So the layer 3, as I said, it's a layer 3, layer 4 technology. The layer 3 packet format is very simple. It's an IP packet. The difference is that for the request, the destination address field carries an identifier, even if it's just a 1 and 28 bits number, while the source address carries the locator. In the case of a consumer socket that is sending a request to reach a producer socket, the source address will be the locator of the interface used by the client sending, well, the host sending a request towards the network. In the case of a reply, the name, so the identifier is stored in the source address field, while the destination address field contains the locator of the previous hop storing a pending request for this data packet. Now you can understand that this way you can essentially reconciliate the request and the replies, because the requests are forwarded in the network by name, so using routing by name in the control plane, while the replies, they are not following the fib in the routers. They're just using the locator information, just like a label swap principle, like similar to MPLS, where the pending request stores the information, so the locator of the previous hop, so that the data can reach back the consumer that was issuing requests towards the producer socket. And that's it. So essentially, there's no other thing that you need to switch hiCN packets. You just need, if everything is just implemented in the endpoints, it's just natural, because if nothing is in between, the producer socket will always receive the request directly from the consumer socket. And so the request will store the IP address of the requester. And so the producer can send the reply back directly by locator. If you have a middle box in between, the middle box is acting as a NAT somehow. In the case of hiCN, you can have as many NAT as you want, because the communication is connectionless. So it's not like in the case of a TCP or UDP when you have to go across a NAT box. It's a little complex because the locators are used to maintain the connectivity between the client and the server, or in general the host, for the entire duration of the communication between the application endpoints. This is not the case in hiCN. There's no connection in the first place. And so every single hiCN middle box in the network is acting as a NAT box by essentially swapping the locators of the previous boxes when the request is sent upstream towards the producer. And in the same way, when the packet has to flow back to the original requester, this is made by essentially label swapping and rewriting the locators into the right field in the packets, in the replies when they flow back to the requester. There is also a layer 4 header. Now we are moving towards a UDP-like header. So as you can see here, we don't need ports to identify and demultiplex application sockets in hiCN. Because the namespace is enough to multiplex and demultiplex connection flows, which is not the case for TCP or UDP sockets. You need ports. For backward compatibility reasons, we keep ports, but they are not something that even if you modify the port numbers, the connection doesn't reset, because the connection doesn't bind, the endpoints don't bind to port numbers. So the layer 4, the only real important features of the layer 4 header is to carry name suffixes. What is a name suffix? The name suffix is nothing more than a sequence number in a stream-like socket. The difference with a stream-like socket like TCP, for instance, is that the sequence number can be anything. So it doesn't need to be a byte pipe. It could be an encoding that is decided by the application. It could be 1, 2, 3, 4. It could be just a random number that only the application endpoint can understand and use to reassemble all the different segments to essentially reconstruct the application level frame and send it up to the application. But that's the only thing you need to remember. There is a name suffix which looks like very much as a sequence number. It is encoded in 32 bits. And if you concatenate the name prefix, which is the IPv6 number, and this name suffix, which is a 32 bits number, you get essentially an unambiguous index in the network to index a single packet if it is needed. So this is where, for instance, this is for reducing redundancy. When you know that the producer socket is serving a huge number of clients because they need to fetch the same data at the same time. This is where you get this advantage, because this information can be shared across a number of users, a number of consumer sockets. Very quickly. So a few words about the authenticity and integrity features I mentioned at the beginning of the talk. You need to imagine that every single reply is carrying signatures, and the signature is a signature that signs an envelope, including the payload of the data packet, plus essentially the names used to index this packet. The name essentially the prefix plus a suffix. You just need to exclude from the signature envelope the header fields that are mutable in the path or that can be modified. So in our implementation, we essentially focus on the only things that we need. So everything in the signature computation is zeroed except the name prefix, the name suffix, and a little more. As I said, optimization are possible. One that we use systematically is the transport manifest, which is a message that carries integrity hashes, SHA-2 signatures, SHA-2 hashes essentially of every single packet. They are packed into this new message, and then the message is signed. This essentially allows to reduce the number of signature computations because you sign just the manifest and not every single packet. This is one example of the kind of optimization that allows you to go out of the very expensive workflow where you need to sign every single data packet. But it's equivalent to it. So even if you don't sign all of them, if you get a packet that is not signed or carrying signatures, the security service of authenticity and integrity is maintained by this kind of optimization. So forwarding path, I think that I may go very quickly here because it could be a little complex, but the only thing that you need to remember from this talk is that the forwarding path of the request and the forwarding path of the replies is not the same. So they behave a little differently. In particular, requests are routed by name. So they are just using the IP fib of the router with a small difference that we add a new data structure into the forwarding pipeline, which is a packet cache. So the packet cache is something that we use to store in priority the requests that are coming from an ingress interface. And we can also store the replies optionally. And the other operation, so the requests are stored to maintain the information of the locators of the requesters in case you get data flowing back into this router, so that you can recognize what was the requester or the requesters asking for this name prefix. The other operation that happens into this pipeline is the NAT operation. Anytime a request is sent upstream, we store the request locally. with the locator information. And when we send it up, we change the locator in the source address field with a locator of the interface that will be used for this transmission. This allows essentially the upstream network to send back the data into this box. That's it. For the data path, as I said, it's a little different and behaves similar to a label swap forwarding, because when you get a data packet back into an hiCN box, you do a lookup, you skip the lookup in the FIB, the forwarding information base of the router. You just make an exact match lookup in this packet cache by using the name that is stored in the source address field of the IP packet. This will give you, as an answer, the locator of all the requesters that previously asked for this name. And so the router can essentially replicate the replies to all the interested requesters. So this is how more or less the forwarding pipeline works. There are some exceptions, like how much time do I need to keep this request packet into this packet cache, and so on. But the core idea is here. There's another functionality in hiCN which is very important, which is punting. Punting is a term used typically in networking Cisco routers to say to redirect the traffic to a specific virtual routing function in the router. Like it could be done by port, like everything with this port can be punted into a specific routing function, or it can be done using very complex rules. It can, for those who are more familiar with IP tables, very similar to those rules, like anything that matches this set of rules should go and be processed by this routing function in the router. So currently, this is an important feature because anytime you want to implement and deploy hiCN, you need to have this punting function in mind. This can be done by port. If for some reasons you need to, your equipment is comfortable with punting based on ports or other things. Our implementation in the Linux Foundation project is essentially a software switch router, so you can do anything you want. But in terms of performance, punting by using IP addresses and ports is highly optimized in today's forwarding pipeline. In network NICs and so all typical hardware offloading but also CPU offloading hardware functions, they are very much optimized for that. And so that's what we do in our implementation. Application support, and then I go to the conclusion, is very important. Like, as I said, there is a layer, which is a set of transport protocols that I briefly described before, but from an application integrator perspective, you focus mostly on the socket API. So hiCN comes with a socket API, which is very different to the iNet BSD socket API you're familiar with, because it's essentially an API that provides a logic which is the consumer producer API logic. So you have data to produce, you produce data under a prefix. You have a data to consume, you consume this data for fetching it by the name prefix. But the transport layer will provide the typical service of a layer 4 function. So segmentation and reassembly, in this case also authentication, verifications of the integrity and stuff like that, which is a service that you as an application integrator, you expect the transport layer will provide. You have application buffers that go into the transport layer through a socket API, and on the other side, you need to receive application level buffers. There are a number of optimizations that I don't have the time to go through right now, but of course, a socket can serve several consumers at the same time, with a number of optimization that can be deployed for the different use cases, where the producer can offload the data distribution to the underlying network stack in different degrees. For instance, as I said, the sender is stateless, So as long as the data is unambiguously indexed by a name prefix and a name suffix, this bunch of data can be stored in different level caches, which can be in the socket, or it could be directly in the network stack of the server or the client, so that the application is offloaded by recopying this data several times from the application into the network stack. So this is one of the optimization that you get from this kind of sockets. So the application is not solicited all the time. The other important part of the application of an application integration is that, as I said, when an application wants to move data from one point to another, the typical operation, you open a socket because you identify either you have already the socket address of the host, or you go through a discovery service like the DNS through a getHostByName API, so that the host name is remapped in an IP address, so that you know the port, and you can open the socket. The application data can move from one place to another. So in the case of hiCN, the operations to map the application into the transfer API is a mapping operation. Essentially, the producer socket has some data, assuming the application has a clear naming or a clear namespace. Not every application has a clear namespace. For instance, even an HTTP server and URI are not a very well-defined namespace for the application. And so when I say here HTTP URI, it doesn't mean that the application is using a very well-defined namespace. In the case, for instance, of MPEG Dash, Dash has a very well-defined namespace, standardized namespace that is, in this case, that fits very well, but it's not the case for many other HTTP-based applications. This is the same for RTP-like application like WebRTC or SIP and many others, where you have a namespace that is very application-specific. But it is up to the application to be aware and knowledgeable about the namespace and the data sources that the application wants to expose into the network. For instance, the case of IPFS, in the IPFS, the namespace is very clear and very well defined. So that when you have to map an application level namespace coming from an IPFS application, it is very well defined. So the mapping of this name into a network namespace is straightforward. Straightforward in the sense that this name in the application layer is permanent. And so while the network namespace is volatile, but when the application decides to use the network namespace, the mapping of this name is unambiguous, because the producer socket will share this mapping across all the consumers that are interested in fetching the application level namespace, because at the application layer, this information is shared. And so there's the chain of namespace mapping is unambiguous and can work for a large set of use cases. So as I said, the producer does the mapping and produce the application level data into the network level socket. And the producer performs the up-to-net mapping and share the mapping through a discovery service, so that the consumer side can be aware of this mapping and use to fetch the data on the other side of the network. So some of the use cases to conclude, I mentioned MPEG Dash. So ADR video distribution is one of the use cases we've been working and we're still working on, where we essentially replicate the machinery that I described in the talk to realize a multicast optimizations to distribute, for instance, live channels in the case of MPEG Dash, by offloading web caches. So this is one example how we are offloading web caching from a very expensive workloads where facing servers have to manage a huge number of facing clients that are pulling the same video at the same time. And so this is an example where ATS is Apache Traffic Server is one web cache, but it can also work for Nginx and many others. typical use case for video distribution. Another use case we've been working on, and we're still working on, is WebRTC and the real-time communication in general, where typically this application in peer-to-peer mode scale very poorly because of the fact that every single peer has to replicate the video across a number of participants. It doesn't scale well also because the peer may have a limited bandwidth at the access network side. And so these systems, they tend to use infrastructure to replicate the media across a number of peers. Now we are working on offloading the infrastructure side so that the infrastructure doesn't need a huge or a significant amount of compute to replicate the media real-time media streams, audio and video, so that this can be replicated in a multicast fashion, but can also take advantage of the load balancing part of hiCN and location independence, where you may have several infrastructure nodes. In this case, this infrastructure node may become simple routers in the case of hiCN. Instead of having full application level routers, they have to essentially interact with the clients. And one advantage in using hiCN for doing that is also end-to-end encryption, in the sense that many of the features that these infrastructure nodes have to provide may require to have a server key for confidentiality and encryption. That is something that may be risky in terms of security, because the application, by using end-to-end encryption, doesn't need to care at all about the potential attacks or risks in terms of leakage of the encryption keys. So this would be essentially something that the application, so the application and service provider wouldn't need to care at all, because the infrastructure node would be just essentially switches and routers. I can skip this use case. A quick heads up about the implementation status. So we are in version 2009. We are following the release. The release is currently available in the Linux Foundation FDIO software. For the network side and transport, we are using very much the VPP, the Vector Packet Processor framework, which is a software framework that allows to implement a very high speed packet processing and also transport stacks. We also support a second stack for the client, which is highly portable. It can support essentially any operating system, including mobile operating system. And we're also working a lot to have different level of control planes for the network, like for network management and telemetry, in particular for troubleshooting. We also support working a lot in mobility management. All I've described focus mostly on scalability and performance of the transport, but all I said is also valid in case of mobility, which is a nice features of hiCN. You can also have multicast and at the same time a user moving across different networks, which is something you cannot have with IP multicast, for instance, one or the other. We're also working a lot in multi-threading, so scaling up a lot the server side of our implementation. In terms of transport, we're working on currently for a lot for real time, but we have a lot of other features, such as for capacity seeking applications, such as TCP-like applications for congestion control, loss detection and recovery. And most recently, we're working on integrating the hiCN transport in the VPP host stack, which is another layer of optimization to get a highly scalable server deployment, especially for the server side. So work in progress, as I mentioned. So we are mostly working internally at Cisco also to support more applications. So not only RTP-like or HTTP-like, which are the two main applications we're supporting right now, but also others. And so we are open to support as many applications as possible, as long as the use cases are relevant. I mentioned here gRPC, which is one we are thinking about, and IPFS, because I'm because I see it as an interesting use case, even if I know just a little about this technology. We're also working, as I mentioned, control and management plane, routing, but also a number of services required by hiCN, such as DHCP for name provisioning, name mapping, and service discovery. And this is it for my presentation.
Great. Thank you so much, Luca. That was wonderful. Let's go ahead and open it up for questions. If you ask a question, of course, you will be in the recording. If you don't want to be in the recording, feel free to type your question into the chat and I will read it for you. Otherwise, let's go ahead and jump in.
Hi, Luca. Great stuff. Great presentation. It was really interesting to see actually the further details you had on mapping between application layer names and how hiCN would handle it. I would be interested to go more into details of that, but instead my question would be, so as you know, IPFS is a peer-to-peer network, so there is, there are issues with NAT traversal. Do you think, like exploiting the features of hiCN would help with, overcoming some of these NAT traversal issues?
So, so one quick answer would be, you don't have problem with addresses or address translations as long as you don't use addresses. And so we don't have big issues in traversing NAT. As I said, so hiCN is designed with locator translations in mind, because every hop is translating is replacing the locator of the previous hop. So NAT is not a problem in itself. What could be a problem is certain types of NAT using stateful NATs using connection profiling. So it's not really the NAT function in itself that is problematic, but is including the Linux kernel, like or the fact that you may have a middle boxes verifying conformancy of the packet stream to something, right?
Yeah.
Or middle boxes modifying in between header fields and stuff like that. But as long as it's just a NAT function, hiCN has no problem. You may also have issues in current NAT in terms of timeouts and stuff like that. For instance, keep alive messages are required to be sure that your stateful NAT has keeps the entry valid in the NAT, but this is mostly for stateful NAT used today in at the edge, mostly, as I said, because you have a connection manager, and so this is also true for UDP, for instance. So this is something that, for instance, we had in the case we're using UDP, so we have to do some keep alive to keep the mapping open in current boxes in the home, for instance. But it's not, strictly speaking, a NAT problem. It's mostly a connection manager problem.
Right. Okay, that would be, I think, interesting to investigate. I don't know how it would play together with the connectionless nature of hiCN. That would be something to consider. In libp2p and IPFS that are mainly, stream oriented, and they keep a connection. There is, TCP and quick support. So I don't know how that would play with hiCN, but that would be an interesting thing to investigate, I think.
Any other questions?
I have another one since no one else has. Have you experimented with applications that do not use some form of traditional DNS to do content resolution? Again, thinking towards IPFS, it's using the DHT. At least one of the ways of content discovery is through a DHT structure. So have you experimented at all with applications similar to that, not similar to that, but applications that don't use the traditional DHT for content resolution?
So the two things that we are considering right now are HTTP-like workloads, and they're mostly DNS-based for service discovery. The other class is real-time communications, and there we tend to use something that is more inside the applications. For instance, in the case of WebRTC, where application discovery, service discovery is typically inside the applications. Well, maybe in the future, with the DNS over HTTP, the DNS is going to be a web service as well. But in the case of real-time communication, most of the time, a lot of the discovery part is inside the applications. Where think about SIP, for instance, and extend this to applications such as WebEx or WebRTC and et cetera. So you don't rely on the DNS for many of the discovery functions, which are built inside the application. So this is another class. For the DHT kind of discovery service, so DHT provides more than just the discovery service. It also provides the routing part. It's absolutely possible to use as DHT. There are other services and networks that have been using the DHT for doing the mapping that we do. One is Lisp. Lisp is, for instance, in some implementation using a DHT, but it's not for doing the mapping I mentioned. It's a mapping IP address into IP addresses, but it's very similar. And so, yes, the DHT is also an option. Definitely can work. Yeah.
Okay, it's interesting. I didn't know about Lisp, actually. I'll have a look. What does Lisp do?
Well, in Lisp, you map host identifiers into
I know what
into locators. And so if Lisp, in the typical deployment of Lisp, Lisp runs in the switch. And so the mapping happens in the switch, which is essentially the element that is doing the mapping, but also encapsulation and decapsulation. So that if the end host is moving, the host doesn't need to change the IP address because the switch is going to do the mapping. The only thing is you need a service for the different Lisp endpoints to resolve the mapping, so that the sockets they don't suffer from the updates in the encapsulation and decapsulation. So
and where is the DHT used? That's why I didn't.
Well, the DHT is the data structure, this decentralized data structure that is stored in the mapping. So that when you need to resolve this mapping, you essentially go into the DHT and get the mapping to update your encap and decap operations.
Okay, cool.
So it's very similar to some of the things we do in hiCN. The distinction is that in hiCN, we do this not from IP addresses into IP addresses, but we do it from application level namespaces into IP addresses. So the network level namespace.
That's great, actually. Yeah, thank you very much. Thanks.
You're welcome.
All right, last call for questions before I kind of read our sign off here and end the recording. Anyone else? Okay, I'll close it up there. If you're watching on YouTube, please remember to hit the like and subscribe buttons and share this video. If you want to suggest a topic or a speaker, there are instructions on how to do that in the description. We'd also have to love you join our mailing list to receive quarterly newsletters, future talk announcements, and information on research funding opportunities. You can do this in the footer at research.protocol.ai. Our next talk is next week, Tuesday, November 3rd at 1700 UTC. Please remember to adjust your time conversions for time zone changes in the US and Europe. I think Europe already happened. Next talk is from João Leitão from the Universidade Nova de Lisboa and the Nova Laboratory for Computer Science and Informatics. His talk title is Topology Management and Gossip, the Way to Scale. Thanks for joining, everyone. We hope to see you next time.